So, welcome student to the next class of Introduction to Nonlinear Optics and its Applications. So, we are almost in the finishing line of our course. So, today we have lecture number 59 and today we will going to learn the nonlinear pulse propagation, and this nonlinear pulse propagation mainly governed by one very important equation or well known equation called nonlinear Schrodinger equation. So, today we will going to derive this equation to understand exactly what is going on when a wave is propagating in a nonlinear medium. So, let us start with the previous class's result, which is the Gaussian wave that is propagating in a linear medium. The linear medium contain the dispersion term, and if we see this is the Gaussian envelope we had, and the solution is of the form this. So, AT is a solution of the pulse envelope at time domain, and in order to find the solution in the time domain, we need to put the information here at this point A 0 omega, which is the frequency of the wave or the frequency component of the wave at z equal to 0 point. Again, that information one can transform with the fact that if the input pulse shape is known in time domain, this is the input pulse shape A 0 t in the time domain, and if I make a Fourier transform of this, then we will have the value of A 0 omega, and if I put this value of A 0 omega here, then we can readily have the solution which will be in this form if the input pulse is Gaussian. So, that was the small exercise I already mentioned in the last class that you should do this exercise, and if you do carefully and correctly, then you will have this kind of expression. So, if you look very carefully this expression, if I compare this input and output expressions, then you will find there are certain changes. One change is here, which is width. So, first width is changing. Secondly, amplitude part is also changing. If you carefully see, if beta 2 is equal to 0, that means there is no dispersion, then the amplitude becomes 1. But if beta 2 is not equal to 0, then we have amplitude, and this amplitude has a real and imaginary part or some sort of complex amplitude. Not only that, the amplitude is also reducing because of this part. So, amplitude is affecting, and finally this entire pulse is having some sort of phase. Here in the input we find that only envelope term is there and everything is real, there is no phase term. Phase means there is nothing related e to the power I phi kind of term. Only thing is that we have a real amplitude here. But if I write this equation properly, this expression properly, then we should have a phase term here. So, phase is evolving. So, we find that even the pulse is propagating in a linear region, the width, amplitude and phase all are changing for a Gaussian input pulse. Now, if I try to find this thing, then I can have some kind of expression of the pulse width and the phase, which give us important informations. This is the pulse shape, Gaussian pulse shape that we had. So, we had the Gaussian pulse shape, and then this Gaussian pulse shape is written in terms of amplitude and phase, as I mentioned. If I calculate this phase, then I will have this term, this big term. If you calculate properly, then you should have this kind of term, where we introduce a new term LD, which is called dispersion length. Dispersion length. LD is nothing but T0 square divided by mod of beta 2. This is the quantity we call LD, and everything is written in terms of LD. This is called the dispersion length, T0 square divided by beta 2. T0 is the pulse width at z equal to 0 point, and beta 2 is the dispersion coefficient. If you carefully look the unit of these things, then LD is since it is a unit of length, because it is representing some sort of distance, then right hand side should be the unit of length also. So, here T0 will be unit of say picosecond, and T0 square will be of this will give you picosecond square, the unit, and beta 2 we know that is a dispersion parameter, and its unit is picosecond square per kilometer. Normally this is the way we represent the dispersion coefficient, picosecond square per kilometer or picosecond square per meter. So, now if I make T0 divided by mod of beta 2, you can see that the unit of this quantity become kilometer. So, that means it is a unit of length. That is why LD basically represent a dispersion length, and this length become very high when beta 2 is very small. That means, if the dispersion effect or dispersion coefficient is small, we should have the dispersion effect at very long distance. That is the physical meaning of these things. Well, if I now look this term, which basically suggests the evolution of the width, pulse width, then you can see that if I increase z, then the pulse width will going to increase. So, if this is my input pulse, which is some sort of Gaussian shape having some initial width, according to our notation it is T0, then after the propagation distance it should be something like this. Amplitude will decay and width will going to increase. This is in time. So, this quantity is nothing but T prime, which is a function of z, and how T prime, that is the width of the pulse, will going to increase is given by this expression. You can readily find this expression if you write this equation in amplitude and phase form as is written. So, as I mentioned, this is given to you as a home task. So, you should do that and just find the wave in this particular form, and you will get this width. After having the knowledge of the width, the next thing is to find out the phase, which is written here, and also we can see that phase is changing, and not only that, phase is a function of time. And now here we find that phase is a function of time and it is a t square. We know that the frequency, instantaneous frequency, we mentioned that in earlier classes, instantaneous frequency, which may be a function of time, is represented by minus del phi, which is a function of time, del t. If I make a derivative with respect to t of a phase phi, then we have instantaneous frequency. But if you make a double derivative of that quantity, then we have something called chirp. Here you can see that this quantity has t square. So, that means I can essentially make a double derivative, and if I make a double derivative of this quantity, I should have something called chirp. So, the chirp basically a function of z here. And what is the meaning of chirp? That means the frequency distribution is not uniform. So, if this is my wave, this is the envelope and this is the wave, this is the distribution of the frequency inside the wave, this is a wave packet, last day we mentioned that. So, this is some sort of uniform frequency distribution. So, if I write this frequency at omega 0, inside the wave packet we have a frequency distribution omega 0. But the same thing if it is chirped, if I draw that, this is the envelope, and for the chirping case what happened, this frequency distribution is not uniform. Some part of the frequency may be small and some part of the frequency may be large when I plot this in time, say t, and it is changing linearly over the time, which basically gives this form. So, that means when the pulse is propagating in a dispersive medium, what happened, that the amplitude of the pulse will go down, width of the pulse will increase, and at the same time the pulse will be chirped. Now, if we remember that what happened in cell phase modulation case, then similar kind of effect was there, and there also we find, if you remember, that was the distribution of intensity, and if I make a derivative of distribution of the intensity, then it was something like this, and based on that we find there is a chirping of the pulse. So, cell phase modulation is the effect where also we have chirping. You should keep in mind that dispersion effect individually gives something which is chirping, and cell phase modulation also gives something which is chirping. Now, with this knowledge we can now have a concept of soliton. So, what happened when the pulse is moving individually in dispersive medium, individually in nonlinear medium, and dispersive plus nonlinear medium both. So, what happened? Let us try to summarize this. So, this is the input pulse in time domain. When it is moving through a dispersive medium, only dispersion takes places, and when the dispersion takes place, then what happened? There will be a temporal broadening, as I mentioned. The pulse will broaden in time domain. So, this is time. Similarly, if the same pulse is moving in a medium where dispersion is not there, only nonlinearity is there, we should have a spectral broadening. The spectra will broaden, whatever the spectra you have, it will broaden. So, here we have temporal broadening, here we have spectral broadening. In this case we have chirping, here also we have some sort of chirping. So, now the idea is, if the dispersion and nonlinearity is put in such a way that they can counterbalance each other, then there is a possibility that this temporal broadening can be restricted as well as this spectral broadening can be restricted, and as a result we will have something where there is no change of pulse shape. This is called the shape preservation. So, I can preserve the pulse shape by adjusting the dispersion and nonlinear parameters suitably, so that there is no change in pulse shape in time domain as well as frequency domain. So, this thing is called soliton. So, soliton is something where the shape of the pulse will remain conserved during the propagation. So, this is a robust structure. So, when a optical pulse is moving in a medium where dispersion and nonlinearity is there, and the value of dispersion and nonlinearity is maintained in such a way that the effects of dispersion and nonlinearity are counterbalanced by each other, then we have a pulse which does not change its shape. So, this is basically the concept of optical soliton. We will learn more about this soliton maybe in the next class, but try to understand what will happen inside the pulse. So, as I mentioned, during the dispersion we have some sort of chirping, and due to the nonlinearity, the cell phase modulation, we have also some sort of chirping. So, here in this schematic plot I have shown that this is a pulse with chirping. You can see that this portion of the pulse is rarefied, that means the frequency is decreased here, but here the frequency is increased. Linearly there is a change of frequency inside this pulse. So, that is called the chirp. But for nonlinearity, what one can do, that they can have a similar kind of pattern of chirping, but in the opposite direction. So, if it is t, it is t. So, here in the leading part of the pulse we have small frequencies, and the frequency get higher and higher in the later part of the pulse. So, exactly the opposite that we have in dispersion. So, if I add these two things, then what happened, these things will be counterbalanced by this one, this part of the pulse will be counterbalance of this part, and as a result we have something where the frequency distribution is uniform. So, that means there is no chirping and the shape of the pulse remain conserved. This is essentially the optical soliton. Well, once we have the idea of optical soliton, now it is time basically to understand how this optical soliton is evolving and what should be its governing equation. Its governing equation is essentially the nonlinear Schrodinger equation. This is a very famous equation. So, in nonlinear Schrodinger equation, what happened, that if I take this equation, which is the Maxwell's equation, from this Maxwell's equation, nonlinear Maxwell's equation, we can derive our nonlinear Schrodinger equation. So, in the previous class we start with this Maxwell's equation, nonlinear Maxwell's equation, and mention that if P nonlinear is 0, I have the equation of motion, equation of this electric field, and this equation of electric field was governed by these two parts. Now, we include the nonlinear part. So, when we include the nonlinear part, what happened? So, this is mu 0 epsilon. So, I can write this epsilon omega as epsilon 0 ER and mu 0 as 1 by epsilon c square, and then I can put this side, and I can write here in this case 1 by c square d 2 E, and then n 0 square E plus 1 by epsilon P nonlinear. So, just manipulating whatever the equation is written, very simple. Then P nonlinear is epsilon 0 chi 3 E cube. Now, E is the electric field. So, if E is the electric field, so I can write this electric field, real electric field in this form. E cube I can write by making a cube, and then I can write it is as 3 omega component, that we have already done when we are dealing with cell phase modulation. Next, if I put this here in this equation, then what happened, that I should have a frequency component 3 omega and the frequency component omega. So, frequency of 3 omega component is basically give us the third harmonic generation part. So, third harmonic generation part we may neglect it at this point, because third harmonic generation requires some sort of phase matching to evolve. So, if the phase matching is not there, which is the case in general, then only this 3 omega part is there. So, E cube is essentially E 0 cube by 4 into 3 cos omega t. So, this 3 cos omega t I can write E 0 cos omega t, which is E, and I can take this E outside. So, another term is there which is E 0 square. So, E 0 square can be represented in terms of intensity. So, if I do all this manipulation, then this portion which is given in the red line can be simply written as N2 square E, where n square E, where n is some sort of intensity, some sort of refractive index depending on intensity, that is important. So, the entire equation become simplified with the fact that now whatever the refractive index we have, it should have an component of intensity. Well, next we will write the equation whatever we derived, and this equation suggests that this will be my equation now to solve. This is the nonlinear equation, and the nonlinearity is introduced here. In linear case, the form of the equation looks quite same. The form of the equation was this, it was just omega, and when refractive index is represented in terms of omega only, that means this is a linear case. So, we were doing the same thing, we are having the same kind of expression even by introducing nonlinearity, but here you should remember that the n is now function of intensity also. Now, we know that whenever we have this kind of equation in our hand, it is easier to solve it in Fourier domain, and if I try to solve this in Fourier domain, which we have done in the previous class also, the technique we discussed in the previous class, if we apply the similar kind of technique, we will find that this equation can be simply written in Fourier domain like this. So, this derivative d2 d square derivative can be simply replaced by omega square, and the electric field is now in the Fourier domain. So, it should be E tilde. So, this equation is relatively easy to solve. So, that is why we write this in Fourier domain. Now, if I want to solve completely, then I need to write the electric field in total form. The electric field in Fourier domain can represent it total form. This is the envelope part, and this is the field distribution. When we write the electric field, so that means electric field should have two component. So, this is my laser light, this is the laser light that is falling on some wall or something. So, there is a distribution over space. So, this space distribution is represented by this r phi coordinate, and also there is a temporal distribution of this pulse. If it is femtosecond pulse, this pulse is distributed in time domain. So, that means some sort of component should be, time component should be there. Here it is written in Fourier domain. So, we have the frequency component, and it has some sort of frequency, and this frequency and the propagation constant, this component should also be there. So, there is a complete form of electric field in terms of spatial distribution and temporal distribution. So, now this grad square operator can be divided into two parts. One is the transverse part and another is the longitudinal. So, if this is the waveguide or the fiber, if I consider this is a fiber, so it is moving like this is the core of the fiber, and if the electric field is launched here, it will move along this direction z. So, there will be a spatial distribution, we call it mode, and along the z it will going to evolve, and this evolution along z can also contain the modal part and the temporal part. So, the pulse which is distribution in time domain can move along z, and we should have some equation for this pulse distribution also, which is in time domain. So, if I now extract these two parts separately, then grad square E I can write simply the derivative. So, grad square is first the derivative with respect to z square plus the transfer component, which is r phi component. So, when we apply that over E, so separation of variables suggests that only the f, this will operate only the f, because f is a function of r phi. So, this quantity will remain outside of the operator. In the similar way, when we make a derivative with respect to z, we should have f r phi outside and all these things here. So, here you should note that when I make a derivative of the quantity this, I should have a double derivative with respect to z, but this quantity is very less than the first order derivative of the envelope. So, we can neglect that. This is essentially the slowly varying envelope approximation. So, when I make a slowly varying envelope approximation, we just neglect this term and we have this term in our hand. So, this is again something we have done before. So, this is not a very new thing. Only thing is that here we are dealing with two different part of the equation, one is related to f and another is related to a tilde. So, now if I write completely to this equation, I will end it up with this, and if I make a separation of variable thing, then I can put this one side and the envelope term in other side. This is a function of r phi, this is a function of z only. So, when these two are equal, then I can write this as a function, as a constant. We call this constant beta. Beta is essentially the propagation constant of a system when the nonlinearity is there. So, eventually we have two equation in our hand, one is the field equation, this, and another is the envelope equation. We will right now we will not bother about this field equation, rather we will try to find out how this envelope equation basically give us this nonlinear Schrodinger equation. So, beta 2, this quantity I can simply write this, which we had done in our previous class. So, this basically simply become the envelope equation. So, 2 beta 0 term will cancel out both the sides, and we will have that. Now, the beta, which is the propagation constant, I can write it in the two part, which is the linear propagation part, and due to the nonlinearity the propagation constant may change, and I write this changing propagation constant at delta B n L. Next, what we will do, we just expand this linear part. So, if I expand this linear part, it will be beta 0, first order derivative of beta omega minus omega 0, second order derivative and so on, plus delta beta n L. Now, beta minus beta 0, if I take up to this, will be simply this quantity, and now I replace omega minus omega 0 to the derivative. So, omega minus omega 0, I can always the last class we have done this, we have shown this, that we can change it to this operator. So, when you change this operator, that means these things I put here. So, this operator is basically will operate over A, which is in frequency domain. So, that means I need to change this A to time domain, because now I change the entire part in time. So, if we do that, then we will have this expression. This is the derivative, first derivative, and this is the second derivative, corresponds to omega minus omega 0 and omega minus omega 0 square term, and delta beta n L will be there. So, now here I have this part, and the rest of the part I write this. We know this because this is basically the transformation that we are looking for, and this transformation is t minus z by V z. When we have this kind of Galilean transformation, we are moving basically the group velocity of the pulse. So, this coordinate is now changing to t. What about delta beta? Delta beta n L is the nonlinear propagation constant, which is the n2 I k 0, and I can write it as n2 omega c effective p, and essentially we will have this expression in our hand. So, let us see what else. So, this basically expression can be now written by putting some kind of rescaling, and when we put this rescaling stuff, we have this p, I can write it as I integration of dx dy, and I again I write in terms of a square, mod of a square, because intensity can be represented in the field square term. So, field square is a square and also this f, and if I write this entire stuff as a constant k, then my rescaling is this. So, if I make a rescaling of this equation, then I will ended up with a shape which is a well known nonlinear Schrodinger equation. So, this is the equation which is nonlinear Schrodinger equation. So, in the next class we will again discuss about the nonlinear Schrodinger equation and try to find out what should be the solution of this nonlinear Schrodinger equation and how this solution leads to optical solitone. So, with this note, let me conclude here. Thank you for your attention and see you in the next class.